Okay, so the goal of today is to explain you some proofs of the rationality of some zeta functions, so in particular in the p-adique and Motivique case. So I hope this morning I will do all the p-adique program and maybe try to explain some outline of the proof in the Motivique setting. And this afternoon we will work on the Motivique setting, and I will explain you some ideas of the proof of a rationality without using any resolution of singularity. So using cell decomposition and quantifier elimination theorem. And if you have time, then I will explain some things which will concern the last talk on the Motivique Milnor fiber. So in order to start, so I will go very slowly and I will repeat some things I explained last week on resolution of singularities and brewing up. Okay, so we start with a basic example. So I consider K a characteristic 0 field. And we will study for the beginning the following polynomial map: x, y, x minus y. Okay, so the zero locus of f is just a 3-line in the plane, and you can observe that you have only one singular point of this curve, and so the critical locus is just one point, which is the point 0, 0. Then I consider the following space Y, which was explained last week, and Y will be a set of points in the plane, and you add also a point in the projective line UV. So this is an element of the Cartesian product of the plane times the projective line, and you impose the following relation, which is xv equal to uy. Okay, and you have a projection to the plane, which is given by the first projection. Okay, so remark. So I denote by H this map. If you look at the inverse image of 0, 0, then you observe in the equation that you have the set of points, so which start with 0, 0, and you have, because of 0 here and 0 here, you have no condition on u and v, so every point on the line are available. So you have this. So this is isomorphic to a P1 projective line. Okay, and furthermore, if x is different to 0, then you observe that for any y in K, the inverse image of the point x, y is the point x, y, and as x is non-zero, then I can divide by x, and then I have an equation for v. So necessarily I will have v equal to uy divided by x. So this is just one point. This is a point 1 yx. So you see that the inverse image of that point is just one point. And also if y is different to 0, then for any x in k, the inverse image of xy is also one point, which will be x over y, like this. So that means that this application H is like this. Above 0, 0, you have a line, and outside of 0, 0, you have an isomorphism. Okay. Each point xy, you have a unique point xy y over x, for instance. Okay, so H, this map H, H is a regular map. And H from y minus the inverse image of 0, 0 to the plane minus 0, 0 is an isomorphism. So that means that this map H is birational. Have an isomorphism between two Zariski open set. And as I said, the inverse image of 0, 0 is a P1, and this is called the exceptional divisor. Okay. So now, if we consider, so in A2 we have our three lines. Okay, so I will write. So I have first line, which is y equal to 0. I have the second line, which is x equals 0, and I have the third line, which is x equal to y. And these three lines are the zero locus of the previous f equals 0. So if I lift these curves in y, I have to just to add a new equation here given by the equation of f. So the inverse image of f equals 0 is a set of points uv such that first equation xv is equal to uy, second equation xy x minus y is equal to 0. So we observe this in the different chart of P1 here. So let's do it. So in fact, no, I will just work on that set, on x and y, but this is the same. So the first case is your point is 0, 0, and then you have the exceptional divisor. So this is isomorphism to P1, and this is the exceptional divisor. Then you have the second case, union, and you assume that x is 0. So if I'm here, necessarily x is 0 or y is 0 or x equal to y. So I start with x equal to 0. So I will have uy equal to 0 here, and you see that I have two cases. The case where u is 0 and the case where y is 0. So I have the exceptional divisor, of course, when y is 0, and I have the other case, union and here I have one line. Okay, so this is E union a line. The other case is similar. So here you have xv equal to 0, and this is E union a line. And the last case, where x equal to y, and here you impose that u equal to v. xv, xu. So you have the exceptional divisor, union xx 1, 1. Okay, so here I have 3 lines, and I observe that when I look at the inverse image, I have 4 lines. Okay, so exceptional divisor and 3 lines. So we do it. So here I have the first lift, here I have the second lift, and then I have the last lift. And what you can observe is that here I have 3 points, and these points are precisely the points which are here. Okay. So, so this is the point 0, 0, 1, 0. Then I have the point 0, 0, 1, 1, and then the point 0. Here. And to come back to the talk of Georges, you see that the point in the projective coordinate here is exactly the slope of the line which is here. Okay? So a point of the projective line is the slope of a line. And here, if you look to the different slope, you see that it appears here. So for instance, here you have a slope 1, and this corresponds to the point of the projective line 1, 1. Okay. So this is an example of a resolution of singularities. So I give you a second example.
Excuse me, why did you insert characteristic 2 at the beginning?
Say again?
At the beginning you said, there was some condition on the characteristic of the field.
Characteristic 0, I said.
Huh? 0, yes.
I just said characteristic 0. So, yeah, just say characteristic 0. So, another example. Is following. So you take, for instance, gxy equal to y2 minus x2 x minus 1. Okay, so if you look at the 0 set, so I said x minus 1, so it's in the other sense. So you have a curve like this, okay? And then if we apply the inverse image of H, we will have, so something like this. So the curve will be lifted like this, and here you have the tangent, the two tangents. And here you have a point A, which corresponds to the slope of this tangent, and here you have the point B, which corresponds to the slope of this tangent. Okay, so this is H, and this is the inverse image of the curves. So if we do computation, this inverse image of G equals 0 will be the set of points. And I have two equations. The first is xv equal to uy, and the second is the equation of the node. So if we work in the chart, u different to 0, then we have so let's call it C. So I can do u equal 1. And I have this and this. Okay. So this is has before a union. So maybe I can. So here I have y in terms of x and y, so I can replace. So this gives you the following thing. So x squared v squared equal to x squared x minus 1, and this equation is x squared factor v squared minus x plus 1 equals 0. So here you can observe that you have a parabola, and here you have the line which corresponds to the exceptional divisor. So this is a union of 0, 0, 1v with v in A1. So this is the exceptional divisor. Union x1, xy, 1v, such that xv is y and v square equal to x plus 1. And of course, if you look at the intersection point AB, so this is an intersection, this will be the set of 0, 0, 1v, such that v squared is 1, and then you have 0, 0, 1, 1, union 0, 0, 1, minus 1. Okay? And these 2 points here correspond to the slope of the 2 tangents. Okay? So here, if you look at when you look at this equation, it starts with y2 minus x squared. Okay, I'm sorry, so we have to work in the complex world. Anyway, so I put 1 here. So if we start like this, so there should be a mistake somewhere in my computation. Anyway, here you have the tangent cone. And the tangent cone gives you the line which are tangent, and you have 2 lines. y equal x and y equal minus x. And when you apply h, you separate the two parts of the curve, and the intersection points are exactly the slope of the tangent line. Okay. So this h, last week we call that a blow up. So this is a blow up. An example of blow up. And if we look in the chart, we observe that, so if I look the composition of f with the blow up on the chart u different to 0, I have an expression in two variables, x and v, and you have the equation x xv, x xv, which is x3 v 1 minus v, and if I look g composed with h in the same chart, I have an expression of the form x squared minus 1 minus x plus v squared. Okay, and you can observe that this composition is a monome times a unit. This is the most important fact. Locally, you have a monome times a unit. Okay, so definition. So you take an algebraic variety over K. So K here, I recall that characteristic of K is 0. So in the following, X will be a affine space. Okay, you take F, a Zariski closed subset. So before my F was F equals 0 or G equals 0. And you assume that F, so if X is not smooth, you assume that F contains a singular locus of X. So it will not be the case for us today. Then an embedded resolution of singularities. Embedded resolution of singularities of the couple X with your closed subvariety F is a data. So given by three things, so Y, E, and H, where, so first of all, Y is a smooth algebraic variety of K. Secondly, E is a normal crossing divisor. So that means, so we will see later in the proof, but which means that locally you can find étale coordinates of of a point, so meaning the regular sequence of regular functions, where some of the functions are local equation of the irreducible components of your exceptional divisor, and the extract functions comes from the smoothness of the total space. Okay, so we will see later. So E is a normal crossing divisor, meaning that locally you look like to an intersection of coordinate plane, hyperplane, locally. You have this, and 3 H from Y to X is a proper map which satisfies that H from Y minus F minus E to X minus F is an isomorphism. And the last thing you want is that the inverse image of F is your exceptional divisor. So for instance, this is an embedded resolution of XF. So here is an example. So I say just a resolution of the plane and the subset F equals 0. Here this is the same. Have an example of embedded resolution of the plane with the curve G equals 0. Okay, so Hironaka proved that in characteristic 0, such an embedded resolution always exists. And for any characteristic, it's true in dimension 2 and 3, and after that, the problem is hardly open. And there is an algorithm to compute a resolution of singularities using, so this is in the proof of Hironaka, using an iteration of blooming up. So theorem, Hironaka. Embedded resolutions always exist for characteristic k equals 0 and can be produced by an algorithm based on iterations of brew-ups. So last week we saw the example of the cusp. So just quickly, I show you. So you have the cusp given by this equation, y2 equal to x3, and you blew up the point. Then you have, as George explained, a line which is the exceptional divisor which maps to the point, and your cusp is transformed in a parabola which is tangent here. Then you blew up again. So you still have your line. You have the exceptional divisor which correspond to that point, of that point, and your parabola is transformed in a line, and then you blow up again. And you have now, you have this. Okay, so you can understand this algorithm of Brouwer just thinking about tangency. Okay, so here you have an important condition of tangency. That means that after one Brouwer you still have tangency, and then you do a Brouwer. So that point gives you a line, and has this line and this parabola have the same tangent. They should go at the same point, which is the same tangent, and you blow up again, and now you have 3 slope difference, so you have 3 line difference. So if you in the chart, and then I go to the p-adique world. In the chart, maybe I should write above. So here, the blow up is given by this changing of coordinates. And you have x1 square, y1 square minus x1. Okay. So I just work in that chart because in the other chart we see nothing. Then I do a blow up again. And so in the good chart, where you have this changing of variables, you obtain x2 square, y2 square, y2 minus x2. So here this corresponds to the line, here this corresponds to that line, and this corresponds to this. And observe that here I have a power 2 and I still have a power 2 here. This is important. This 2 will be the multiplicity, and the multiplicity is preserved after blowing up. So I continue. If I do the third Brouwer, so here we have to look at the 2 charts. So in that case, in the first chart, I have this, and this gives you x3 square, y3 6, 1 minus x3, and in the other chart, x2 equal to x3, y2 equal to x3, y3. I have another thing. I have x3 6, y3 3, y3 minus 1. So again, in that chart, I see only the red and the yellow. I see the red, the yellow, and the white. In the other chart, I don't see the red, I only see the blue, which is given by this equation, the white, and the yellow, and the white. Okay. So this is important because you see that, so this is at the end F composed with H in some open. And here this is F composed with H in another open set. And you see that locally you have a different form. Okay? But which is very important that you still have the same multiplicities. So 2, 2, 2, and after you have, this is a 3. 3, 3, and you still have 6. Okay, so now we can start the proof of the rationality of Iguza's zeta function. I will use that to do to transform the problem of an integration in a problem of an integration of a very easy functions. Okay, so maybe 2. So I recall the notation. So I start with a polynomial with integer coefficients and d variables. I fix p a prime number. And for any n, I denote by fn the cardinal of the point so in that ring, such that you have a solution of f modulo p to the n, and we have denoted by GPT the zeta function sum for n larger than 1 f and t. Okay. So then the idea of the proof of the rationality of GPT by Guza is first to transform that to an integral over p-adiques. So facts, first fact, maybe definition before. So the p-adique Guza zeta function is defined by, for a positive real S, ZFP of S is integral over ZPD of f dx, and this is the sum for m larger than m positive of the Motivique measure of the integer p-adique points, p-adique vector, which the p-adique order of fx is equal to m, and here I have p minus ms. So the fact is that GP evaluated in P minus S minus D is equal to P minus S divided by 1 minus P minus S, 1 minus the zeta function. So that means that to study this Poincaré series, it's enough to study this p-adique integral. This is the main idea. So the proof is very easy, using properties of the measure. So first of all, you can observe that I replace t by this, and I have the cardinal of x in z p to the n c over d, such that fx equals 0 modulo pn, and then I have p minus nd, p minus ns. And then, if you remember what I explained last week, we can interpret that as a p-adique measure. Okay, so this is for n larger than 1. So this is the p-adique measure of the p-adique point which satisfies fx equals 0 modulo Pn. This is by definition. So I can say that this is the sum for n larger than 1 of the p-adique measure of ZPD minus the disjoint union of XL for L running from 0 to n minus 1, P minus NS, where here I define this set as XM. So here you can replace that by the p-adique order of fx is larger than n. You can replace that. To be equal to 0 after truncation modulo Pn means that you have an order larger than n. So you can replace this by the measure of that set. Okay. And then using the measure, you have a sum for n larger than 1. So I recall you that the p-adique measure of the unit ball is 1. So this gives you 1 minus the sum for L equals 0 to n minus 1 of the p-adique measure of XL, P minus NS. And then you can do you can change the order of the sigma, and you will have this minus the sum for n that is equal to the sum for L positive for sum for n larger than n plus 1, P minus NS, p-adique measure of XL. So you have this equality. So this gives you the formula there. Okay. Okay, so it's just a game of measure. And then we will concentrate on the rationalities of this function. P-adique equals the function is a rational function P minus S. Okay, so I consider f in with integer coefficients, but more generally, you can start with f with p-adique coefficients, and I consider z inside Q, inside QP. So if I take so I consider f has a function from the fine space over QP to the fine life of a QP, and I consider H an embedded resolution. So E is the union of EI, which are irreducible components, indexed by a finite set. This is the inverse image of f equals 0. And then, as we have seen in the previous example, the divisor attached to f composed with h has some multiplicities. So usually written like this. So that means that locally, in some open set UI, you have, so maybe I should say, locally, f composed with h will have the form a unit times a product of yi and I, like this. So this is a unit. And this is ethyl coordinate, where locally yi is an equation of the reducible component ei, and you have also a Jacobian due to h. So you have a Jacobian divisor of h, which is supported by the exceptional locus, because H is an isomorphism outside of the exceptional locus. So the Jacobian of H is supported by E, and it has also multiplicity, which are written like this, mu I minus 1, EI. That means that locally, the Jacobian of H is a unit times the product yi mu I minus 1, I in capital I. Okay. So we will use this expression locally. So this mu I minus 1 is at the beginning a bit surprising, because why we put here a minus 1? But you will see, for instance, in the Motivique case, that this minus 1 will disappear and will give you at the end a very nice formula. Okay. So you will see maybe this afternoon or before this morning. Okay. So these multiplicities ni and ui are called data of the resolution. Okay. So let's do the proof. So I recall you some things. First, in the p-adique integration, we have a change variable formula. So we will use it now. And of course, H is not an isomorphism globally, but outside of a zero measure set, it's an isomorphism. So it has sense to say that. Okay. So you have this kind of formula and a remark. So this is a p-adique change variable formula and a remark. As we have seen last week, ZPD is a ball with a relative radius 0. And as I explained you, the balls are compact. Is open and compact. So as H is proper, is continuous and proper, then the inverse image of this ball is open by continuity and is also compact by properness. So it's important because above we work on the compact set, and so we will use Borel-Lebesgue property to have finitely many open sets. Okay. Proper means that the inverse image of any compact set is compact in that case. Okay. In this afternoon, we will use it in algebraic geometry, and then the definition is different for that, and we will see what we need. Okay. So then, there are finitely many open and compact sets U in so they are disjoint. So I recall you that QP is totally disconnected. Okay. Such that I have to draw a picture. Okay, so this is the situation here. And then what I'm going to do is to consider a covering of H-1 ZPD by a disjoint union of open set, okay, where on this open set I have a local form like this. Okay, So such that, so just I explained that for this morning, but I will need it this afternoon. You have a stupid, a trivial stratification of E. Usually we wrote it like that. Where EI0 is the intersection of element in I minus the union minus this. So for instance, in that case, you have two components, E1, E2, okay? So you have the first E2, 0, the second E1, 0, and then you have the intersection, which is E1, 2, 0. So this is a stratification in three pieces here. So you can do it for this. So such that the intersection of your open set with the exceptional divisor is an intersection with some stratum here, and I rewrite again. I have this this equation. Okay. Where yi for I in I is a regular sequence of regular functions on U, and where EI intersected by U is given by the equation yi equals 0 for any I. Okay, so we have this. And now, the thing which is important is, well, is that point. They are disjoint. That means that I will apply the shell relation here. Okay. So I split my integrals on the sum of integrals over there's U, and I will replace that function by this, and that function by this, and then I have an easy integral to compute as last week. Okay, so just some technical details. So we can assume, so as U is compact and the valuation is discrete, we can assume that the absolute value of U and absolute value of V are constant on U. So U and V are units. Huh? So they have finitely many values because U is compact. So up to splitting U, you can assume that they are constant on U, and the order of U can be equal to A, and order of V can be equal to some B. And then we have over U, you have this. Product for 1 to R. Okay, so we arrive to the kind of things. So now we want to compute this. And then we will sum about on all of this integral. So we can complete this sequence, the sequence yi for I from 1 to d, and this gives. So here we work in the analytic world. So we have in the algebraic world we will just have an étale map, but in analytic world we will have a bianalytic isomorphism. Maybe I should say injection. From U to no, I can say isomorphism, but just I have from U to his image, include in AD QP. Okay, so U is open and compact. So that U is also open compact. And here I live in this wonderful affine space, so I will split this phi as a union of bolts. Okay? In that way I can integrate only on bolts, and then I know how to do. Because I recall that this U lives in some algebraic variety Y. So using this change of coordinate, we will work inside a very nice affine space and do computation. So we can assume up to splitting phi U to be a ball. Okay, and then by identification, we can assume that U is a ball, a polyball. I say no, just a ball. Okay. And then you compute by Fubini theorem. This is the product of the integral for order of yi larger than m and last week I explained you the computation of these integrals, and we obtained p minus m n I s plus nu I divided by 1 p minus m p minus n I plus n I s plus nu I. So this is a rational function in p minus s multiplied by an element in the form p minus s times something, and you have to sum up all of this on all the u, and as this is compact, you have finitely many terms, and this gives you the rational form. Okay? So by additivity, we can conclude. So the remark is additivity we have proofs that the zeta function of f is something like a sum over the components of A of a finite over some parts of all the parts except empty set of A. So of course empty set can be considered in another case, because can be considered alone because H is an isomorphism, so it's not a problem for that. But you have a sum of some things times a product this m is the order of the ball. So you have something like that. So this form is not very concrete, okay? But it gives you an idea of the sum. And in fact, Denef, and I will conclude during the 10 minutes, Denef gave a very nice formula in terms of the resolution for some p where we have a notion of a good reduction, modulo p. It was done in 87. So I consider f with z coefficients. So this is important. and I consider an embedded resolution in Q, with data and I nu I. Then I've proved that for almost all prime p means all p except finitely many. We have the following formula. So p minus d, so d is the number of variables. Sum for I including a of the cardinal of EI0. So this bar means the reduction modulo p of the component EI0. So that means that you have equation locally and you reduce modulo p all the equation. Okay? And there is a notion of good and bad reduction, and this almost all prime p means a good reduction. So you have this cardinality which happens, and times a product for I in I of p minus 1, and you have p minus nis minus nu I divided by 1 minus p nis. So you recover the power which were here. You recover it. They are here, and you have a multiplication by p minus 1. So just a remark, and then we stop. So the formula hold. For all prime p, such that the reduction mod p of f is not 0, is not 0 in the ring of polynomial function with that with fp coefficients, and the reduction modulo p is good. I should say the resolution H has good resolution but p. So what is that? First of all, when you take the reduction modulo p of y, this is smooth over the finite field fp. When you look at the reduction of the reducible components of your divisor, it's also smooth. The union is still a normal crossing divisor. And when you look at the reduction modulo p of two components, maybe you should have some irreducible component which appears after reduction mod p, but you impose that if I is different to j, then there are no common irreducible components. Okay, so you have bad reduction, you have a good resolution, good reduction mod P. If you have this, and in fact, we can prove that the set of prime numbers such that you don't have a good reduction is finite. So if we don't care about them, then we have this formula. And what we will prove this afternoon is a Motivique, the Motivique version of all of this. And you will observe that we have exactly the same formula, replacing that by a class of these components. And then you have a Motivique specialization, which will replace, which will map L to P and the class of the in the Grothendieck group, Grothendieck ring, to the cardinal of the set reduced modulo P. So you have this kind of universal principle, which we will observe in that zeta function. Okay, so I stop here.